So guys, you once again welcome to FIL Builders Bootcamp for our virtual participant. Welcome once again, and the guys in the house, welcome. And we also have one of some of our speakers on the call. I'm going to allow Femi to introduce himself. So we're doing this um, yeah, as a road map, a road walk from the FIL Lagos event. So we want to like take some time out and get to understand some of the technologies in the Python ecosystem. My name is Chikemeka Baby, if you're just joining. And I lead the Python Orbit Africa. So, and we recently had a FIL Lagos event on Tuesday, which was successful. And we're very happy with the turnout, with the curiosity, the interest. Um, it was possible with the help of some of the Orbit ambassadors as well, who tuned in, and some of the great speakers who graced the occasion. So we won't be slowing down. We'll be doing a whole lot of activities that will help the community and as well you. So as you all know, this week is really a Web3 week for Africa, all the way from started from Ghana, Nigeria, South Africa, Kenya as well. So the ecosystem as well is not also slowing down. So we want to see how we can get more guys on the ecosystem build and bring out innovative solutions that are simple, usable, and scalable. So, Femi, we're happy to have you, and you have the floor now. Thank you.
All right. Good morning, everyone. My name is Temi. I am a software engineer and also a Filecoin Orbit ambassador. So I work on the blockchain. And today, I think we'll just go through or have a rundown on tools to build on the FVM. I think that's the major thing we can have today. And basically, maybe a little intro to Solidity as well. I think that should work. So I'll try to share my screen as well. All right. Can you see my screen? Hello, can anyone hear me?
Yes, please. Yes.
Okay. All right. So, basically, I don't know if I should give a reintroduction to Filecoin itself. I think a couple of us might know what Filecoin is, or should know what Filecoin is. But then I would basically just give a run through of Filecoin itself, the FVM, which is Filecoin's EVM based blockchain or EVM compatible blockchain, and then the technologies Filecoin provides. So, Filecoin, which started, I think, sometime in 2016 or 2017, started with IPFS as a decentralized storage solution company. So IPFS was the first solution provided by Filecoin, then targeted basically decentralized storage for users running on nodes as well. And then later on went on to have their token as well, which today we know as the FIL token, Filecoin token. And then that serves as a reward for storage providers on the IPFS and Filecoin network. So there's a native blockchain, Filecoin itself, where the Filecoin token itself started from. And then currently we have the FVM, which is a virtual machine built on Filecoin. It's an EVM compatible blockchain. So basically provides computation access to data that's been stored on Filecoin previously. So currently the Filecoin virtual machine is a runtime environment for smart contracts, also called, sorry, did someone say something?
Yeah, please go
Okay,
on. Everybody mute your mic, please. Thank you.
no worries. So the Filecoin virtual machine is a runtime environment for smart contracts. On Filecoin, they are also called actors. Then FVM brings user programmability to Filecoin. So previously or before FVM itself was launched or worked on, you could basically store and retrieve data from Filecoin um, using IPFS, of course. But now we have the opportunity to actually run computation on this data that has been stored using the current FVM blockchain. So basically tools that you can use to build on FVM itself, which would be going through or having a rundown. Okay, before we go to that, here's the Filecoin, the first solution. So this basically the decentralized storage network, and then the FIL token is also serving as an incentive or a reward for data providers, storage providers. All right. So tools we can use to build on Filecoin. Currently on the FVM, it supports Solidity, which is the primary language for smart contract development on most EVM compatible chains. So if you've worked on blockchains like Ethereum, um, maybe Polygon, Optimism, the primary language that would have been used on those blockchains is Solidity, and it can also be used here out of the box. So also with tools like Hard Hat, which is for smart contract development and deployment on the blockchains. then other tools like Foundry and a couple of others. So going through Solidity, I think for today would most likely learn directly through the Solidity documentation and books. So we'll be following through with their docs, and then I'll be explaining as we go on. Right. But before then, here's more of a technical explanation of the FVM. So currently the FVM is WASM based. So one advantage of being WASM based is that various programming languages can be used to deploy um, smart contracts on the blockchain, so far as they all compile to WASM. So far as they compile to WASM code, any language can be used to write a smart contract on the FVM. Although this is still in beta mode, it's not fully functional and not stable yet. So we're not going to be making use of anything related to that now. And then FEVM compatibility. This was what I mentioned earlier about compatibility with EVM and every language that has been useful for other EVM blockchains. And then VM agnostic. So other foreign VMs can be integrated into Filecoin later on. So since Filecoin is basically a storage company, a decentralized storage company, the various use cases that have been outlined to us are um, solutions related to storage, related to data. And here we have data DAOs, we have data access controls, we have perpetual storage, we have replication and leasing. So one notable benefits of Filecoin and the decentralized storage is the fact that all data stored on Filecoin is available consistently over time. So let's say the data literally lives forever and cannot be deleted or tampered with on Filecoin. So that's one advantage to Filecoin. So I'll just go towards, yep, smart contracts. So developing on Filecoin, we've gone through what Filecoin and IPFS itself means. We've gone through what the FVM itself means as well, and then tools that would be useful to us while building. So to deploy a smart contract on FVM, you need an RPC, or you can use your MetaMask wallet so far as you have the Filecoin network connected or on your wallet, MetaMask in this case. And then for our development, all development we'll be doing will be on Remix. Remix is the decentralized IDE provided by the Ethereum Foundation. So, I think, yeah. All right. So I mentioned earlier that we're going to be learning from the Solidity documentation. So I'll also open that on the side. All right. So um a couple of resources that would also be useful would be shared on maybe by I'll send them to later on, and then we'll have them sent across. So for tools that are useful in our case here, we, as an alternative to Remix, you can use VS Code or any other IDE, and then you can deploy contracts using Hard Hat or Foundry, whichever one works or whichever one is more comfortable for you as a developer. So Solidity files are stored in a .so file type. So the same way for JavaScript, we have .js, for TypeScript, .ts, and all others. We have .so for Solidity files. So you can create a new file. Let's say hello world.so. Right. So when writing Solidity code, the first thing that we usually do is to declare the Solidity version in our file. I don't know if anybody's following through. Is anybody following through?
Yes, we are following you.
Okay.
Hello.
Yeah, I can hear you. Hello.
Yeah, we are following up. We are following up.
Okay. All right. All right. Okay.
We can hear
So,
you loud and clear, sir.
all right. All right. That's fine. So I was mentioning that on or in Solidity, the first thing we usually do when we're writing a Solidity program or writing a smart contract is to declare the Solidity version we're using, and then the license that we are using for the specific program. So I think we can do that with, yeah, I'll just declare an SPDX license for a GPL. Okay. All right. And then I would also declare the Solidity version I'll be writing in. All right. So basically what I did here was the first line here is an identifier for the license which we are developing on. And here we are developing on a GPL license. And then the second line here declares the Solidity version that we are planning to deploy or build with. So this is an identifier, the pragma directive. And then this set of numbers here show that the contract we are going to be developing is valid between the Solidity 0.4.0 version and then 0.9.0 version. So it also helps our compiler to know what version of Solidity we are running on. or version of Solidity it can use to compile our smart contract. So next thing we do is to declare the contract itself. Okay, so let's say contract hello world, and then we use curly brackets to save that. So Solidity itself is a curly bracket language. So now we've declared the contract, and then before we move forward, I think we could just go through the different declarations we could have. So I'll show examples from the Solidity docs itself. All right. So the different value types we have, like in every other programming language, we have booleans. So I don't know if any of us is familiar with other programming languages, something like JavaScript or TypeScript. So in all those other languages, we have booleans. So booleans basically are true or false constants. And then we have integers. In Solidity, we use uint or int for integers. And then we have different versions. We have uint 8, uint 256. This is to show our smart contract basically the size of the integers we have. So integers are basically signed and unsigned numbers of different sizes. Then for the different operatives we have addition, subtraction, multiplication. All this can be done on the integer type here. So all these are also operatives that can be done. So we also have address. So basically this holds a value of an Ethereum address. And then address payable shows that the same address has the ability to transfer or send tokens. So next type, the contract types that we have. So we have the payable. This shows that the contract itself has the ability to receive and send tokens. So we also have arrays. So in all programming languages, we have some function or some implementation of arrays. In JavaScript, in Golang, we have arrays as well. So this basically hold up a struct of numbers, a struct of data. It could be strings, it could be integers. Different types of data can be held in arrays so far as you declare what type of data it is. Then we have strings. Strings basically can hold up any data, but then have to be declared or have to be shown using quotation marks. Okay, so those are the basic value types we have in Solidity. Yeah, I don't think there's any other we have to go through now. Okay, structs are advanced data types in Solidity, so I think we could come to that later on. The same with objects in JavaScript and similar languages. All right, so we can go forward with the contract. I think here we're going to try to work on a simple hello world contract. So that's usually the first point of entry to smart contract development for most developers. All right, is anybody still following? Okay, let's just move on there. So let's remix. All right. So in our contracts, we are going to declare the string, and then the next, which I'll write here, is public. This is to show that the current string is a public keyword. Then great equals to hello world. Then we'll also save this and end with our semicolon. So this basically is a hello world string written in Solidity. If you've followed a couple of tutorials in maybe JavaScript, the first thing that we usually do is hello world. Then you can log that to your console or whatever you want to do. But then in Solidity, every contract must be compiled. So here we can compile whatever contract we have, in this case, hello world or so, which basically doesn't do much currently. So, and then you can deploy and run. So while learning or while building locally, we can deploy to the Remix VM before we later on deploy to the Filecoin testnet. Right. Okay. So this is a basic hello world contract. Then we can go on to try new things on Solidity. Let me showcase maybe deploying this contract on a simple Remix VM. Okay, this has been deployed, and then we have our contract address. So every smart contract on an Ethereum virtual machine is identified by a smart contract, which is literally an address similar to your wallet addresses. So if you've interacted with any Ethereum based blockchain, you have your wallet, which is 0x and then a series of numbers or letters. So in this case, the wallet address itself is 0x5b and then a couple of letters and numbers. And then we have the contract address for the contract we just deployed, which is the 0xd9 and then a series of numbers and letters following. So that was basically an example of an Ethereum wallet address or an Ethereum contract address. So we've deployed this contract and we can view it on this contract address on our local Remix VM. So let's go forward and try to write a simple contract following the Solidity docs. All right. So let's go through the structure of a smart contract. So basically the basics of whatever contract we can be deploying on our blockchain. So here we have the state variables. So these are variables that are permanently stored in the contract storage. This is one of them, the license identifier, and then the pragma identifier. So pragma specifies the compiler version for the code we're going to be writing. I've explained this before. Then this is our contract name itself. In our case here, we used Hello World for our contract name. And then here, uint. So if you remember earlier, when we looked at integers, we saw that integers could either be int or uint. So this is a stored state variable. So next we have functions. So in all languages, functions are chunks of code that can be executed. So in maybe a program to get user data, you can have a function named maybe get user data. And then that function, whenever it's called or run, you can view user data, or it can retrieve user data from whatever storage you have. So here we see that functions are executable units of code. They are usually defined inside the contract, but they can also be specified outside of contracts. So here we have a function. The functions are declared with function, then the function name, and whatever it takes in. So we have function, in this case, bid, and then a set of brackets. In this case, it's empty, which shows that the function itself doesn't take in any data. And then we have public. This shows that the function is public. So it doesn't only compile or run internally. It can also be compiled. It can also be compiled and interacted with by the public. And payable, I mentioned payable earlier on, which is that this can transfer or send tokens. So outside of our contract, we said functions are usually defined inside the contract, but can also be defined outside of the contract. So this function bid is defined inside the contract simple auction, but then can also be defined outside of the contract, although it's not going to be essential to the contract itself. But then we have helper functions. In this case, we see function helper and then takes in an integer and then returns also another integer. So a helper function. So in this case, the integer we received, we assigned it the value x. So we named it a variable x. And then in the function, we returned the value x multiplied by 2. So this is a helper function that multiplies whatever value is being sent into it. So if you call this function and pass in maybe the number 2, it returns 4, which is 2 times 2. If you call it and pass in maybe 3, it returns 3 times 2, which is 6. So these are functions. So functions can accept parameters, whatever types of parameters you have, not only integers. So you can have a function that takes in an address as the parameter. You can have a function that takes in a set of arrays. You can have a function that takes in a string and literally any variable as the parameter. All right. So next we have function modifiers. So function modifiers can be used to amend the semantics of functions in a declarative way. Basically, you can use this to work on a function that has been declared earlier. But mostly, these modifiers can be overridden by the function itself. So this example here is an example of a contract named purchase. So in this contract, we defined the solidity compiler version 0.4.22 to 0.9.0. then declare the contract purchase. We declared a couple of variables. In this place, we declared address, which is also a public variable. And then the modifier here. So this is a modifier called only seller. So this modifier itself makes sure that only the seller, which is an address that has been specified before, can call this function. So that's an example of a modifier. Next we have events. So events, if you worked with other languages where we have WebSockets and then we emit events from whatever has occurred in the contract or in our code. Here we can also emit events. So in this case, we have an event named highest bid increased. So if you notice, all the examples we've had on the Solidity docs here are related to sort of an auction program. So you can see here we have the simple auction, and then all the other related examples have been maybe purchase, and then here we have simple auction as well. So we have an event named highest bid increased. So this is emitted whenever the highest bid on the auction has been increased, and then also emits the address of the bidder, and then the current amount which has been bidded for. Yeah. So events are declared and can be used from whatever DApp we have. DApp is short for decentralized applications. So we also have errors. So in most languages now, we have errors which can be used for maybe failure situations. So we have a code or a block of code, is the correct way to say it. If we have a block of code and then we run a function, but we maybe come into an error, the function is not successful. Maybe you try to bid for an item on the simple auction side, and then you do not have sufficient funds or sufficient tokens to purchase or bid. You can declare an error. So in this case, declare an error with the keyword error, and then the error name, and then the things that are emitted by the error. So in this case, we have error, not enough funds, and then it shows a uint, an integer, for the requested value, and then also shows an integer for the available value. So in this case, the requested value is the amount the wallet address tried to bid, and then the available is the current available for tokens in the bidder's wallet. So we have structs. So I mentioned earlier that structs were advanced data types that we're not going to look at earlier on. But here, structs are similar to objects. So they can house various data types. If you've worked with JavaScript and maybe seen object-oriented programming, you would see that you can declare an object, maybe an object, let's say a person now, and then you can declare the name of the person, maybe a string, maybe the age of the person, which would be a number, and then maybe let's say hobbies, which would be an array. So you can declare that under an object and then reuse that object data later on. So this is also possible in Solidity, but we call them structs in this case, not objects. So we have structs here, and in this case we have a struct named ballot. Sorry, a struct named voter. So for that voter, we can have different values or different variables. So in that struct, we have the weight of the voter, which is an integer. We have voted, which is a boolean. This is a yes or no value, which shows whether the voter has voted. We have delegates, which is an address value, and then votes. So how many votes the user voted in, the address, whether the user has voted, then width. So up next, we have enum types. So these are more like data types that are custom created with specific values. So these constant values cannot be changed. And if you've worked with other languages and used maybe something like states, these are very similar to states. And then we have an enum called states. And then these are the possible values of the enum type, which we created here. So we have created, which is one type. We have locked, and then inactive. So this specific enum can only have these three values. So either of these three values at once. And up next, let's go to different types. We've gone through types earlier on. I'll look at the different data types we have in Solidity, and then operations that can be carried out on these data types. All right. So these are globally available variables. So on every EVM, we have this set of variables that are constant. So Ethereum or Ether is the basic unit on every EVM chain. So Ether units can be either Wei, which is the smallest denomination, and then Gui or Ether. So one Wei is the smallest possible value on an Ethereum blockchain, and then Gui is a subdenomination of Ether, and then one Ether is one Ethereum token or one Ethereum value. So we also have time units. These are also globally available. So we have seconds, minutes, hours, days, and weeks. So you can use this in your smart contract. Maybe for the auction now, if you want the auction to last an hour, you can declare the time, the valid time for an auction to be 1 hour. So we have special variables. So we have block hash, which is the transaction or the block hash of a specific block. Then we have block base fee, block base fee. I would not explain all of this, but I'll try to explain the ones that are useful to us currently. So we have the block.chain ID. So if you've worked with any Ethereum blockchain before, or if you've interacted with any blockchain before, you'll notice that we have chain IDs for all Ethereum-based blockchains. So the Ethereum chain itself is number one. So it assumes a chain ID of 1. And then we have gas limit as well. This will be useful to us. So for every transaction, there's a current gas limit that cannot or must not be exceeded, or else the transaction would fail. So this is block or number, which is the current block number. Then block or timestamp. All right. Then we have message.data, which is the complete data being sent into a transaction. We have message.sender, which is the sender of that current message. We have a message of value, which is the number of way. Remember I mentioned that way is the smallest value of an ether. And then gas price. This is after the transaction has been successful. You can view the gas price, the amount of way or amount of ether that was used as gas. All right. So in Solidity development, there's what we call ABI. So this is provided to us on compilation and deployment of a smart contract. So ABIs help us to interact with whatever smart contracts we've deployed. And ABIs can be interacted with in different languages. So far as you have a contract ABI, you can interact with it in Go, you can interact in JavaScript, different languages. All right. So let's go back to our initial contract. Okay. Structure of the contract. So maybe let's try to write a smart contract. All right. So let's try to work on a smart contract with a couple of functions. So we'll implement a counter contract. Let me open this. So we'll create a new contract file. Let's call it counter.so. And then what we are going to do on, oh, sorry, created the folder instead. All right. So what we want to achieve with our counter contract here is a simple contract that you can use to get the count stored. You can increase the count stored on the contract and also decrease the count stored. So we're going to declare the license as usual. Yes. No. In this case, let's try an MIT open source license. Then would have our pragma identifier, which declares the Solidity compiler version. So I'd use another Solidity version here, 0.8.26, and then I'll explain what it does. So this Solidity version here tells our compiler that we are working with only Solidity code that is above the 0.8.26 version. Right, then we go forward to declare the contract. So for every contract that we are declaring, we use the curly bracket to initialize the function. And then we can write whatever code is going to be executed in the contract. Before moving forward, give me a minute. All right. Let's continue with that. So we've declared our contracts, and then we're going to declare variables, perpetual variables. So remember, we are going to be making use of a count. So we'd have to declare the count itself. Let's use UN 256. And let's also make the count a public variable. Then we'd also declare a function to get the current count. So we'll declare the function with the function keyword. Then let's call the function get. Since we don't take in any variables, we'll leave the variable bracket empty. Then make the function a public function. And then the function returns an integer. Then we can go on to initialize the function. Then it returns a count. So this count here is this variable. All right. So we are returning this count here, the count we previously initialized. And then let's go on to declare another function. So the next function we'll declare is to increase the current count by 1. Then we'll declare the contract, of course, using the function keyword. Then increase. Let's also make that public. Then initialize the function. So what we need here is to increase the count by 1. So what we did here, we are running an operative on the count. So this is plus equals to 1. And then what this does essentially is to increase the current, whatever the value of the current count is, we're increasing it by 1. So if we wanted to increase it by 2, we would change this to 2. If we wanted to increase this to maybe 100 itself, we can increase it by 100. But working with 1, then let's write a function to decrease the count by 1. We also have the function decrease. Let's also make this publicly callable. Then count. Then since we had plus equals to for incrementing, we can use minus equals to decrease. All right. So this is basically the contract to store, increment, or increase, and then decrease the current count value. So we can compile and deploy this on our current local blockchain, and then also interact with it. So let's compile this. Then we can also deploy. So here we have the contract address, we have the block hash, we have the transaction hash for the transaction we sent, and then the output. Then we would also have our ABI compiled and stored here. So this is the transaction ABI or the contract ABI, which we can use to interact with the smart contracts. So this is the ABI, and then these are functions we can use. So we have count, which is the variable. We have decrease, which is the decrease function. Then we have increase, which is the increase function. So let's interact with our contracts. Right. So we can get the current count, which is 0, since we've not done anything. We've not increased the count, we've not decreased the count. So let's try to increase the count. So this has increased the count by 1, meaning if we call the count, we should have 1. All right, so this is 1. If we increase the count again, if we call the count now, we should have 2. Anybody following? All right, so let's decrease the current count by 1 and then call again. So initially we had 2 here, If we call again, we should have one count in our smart contract. So this is an example of a simple smart contract that can be deployed and then interacted with on the blockchain. So we have functions we can call, then we have functions we can transact with or interact with on chain. Now, did anybody get that? This is the
We
current
are
house
following
by
you.
one, and then call it again. So initially we had two here. All right. So let's try to deploy this on the Filecoin testnet network. So I'll reshare my screen with a window that has MetaMask on it. Okay. All right. So we're also going to mix the agenda on, sorry, Ethereum, that's all. And on our contracts, we're going to, I'll copy the contracts from the previous one we had. Now let's try to deploy this contract on the Filecoin virtual machine testnet. We'll try to do that using the calibration testnet. So here we're going to change our environment. If you noticed, we've been using the remix VM here, but we use the injected provider and then connect our wallet. I'll just make sure I'm on, okay, yes, I'm on the Filecoin calibration testnet. And then I've compiled the current contract, so I'll just try to deploy it on chain. For some reason, It's not showing my wallet address. So let me disconnect and reconnect it. All right. Okay. So let me compile again and then deploy. So I'll confirm the contract deployment. So the contract is pending. So while that's pending, I'll open up our blockchain explorer and then try to follow it up. Let me use Firefox instead. So this Chinese. All right. So I can see our latest transaction, which is this. So our contract has been created successfully. Now let's go back to Remix and try to interact with our contract. So here's our own contract address, which you can access on the blockchain. Let me open collaboration.field. All right. And then I can go to our new contract address here. So let's try to interact with this contract. So here's our deployed contract. Let's try to increase. Okay, let's get the current count before we increase. So current count is 0. So let's increase. We'll confirm our transaction. Pending. Okay. Our transaction is still pending. Still pending. So while that's pending, so the function to get current count does not require us to confirm a transaction on the blockchain, since we are not directly making any changes. We're only getting the current value. But then our functions to increase and decrease counts would require us to confirm transactions, since we are directly changing the value of something on the blockchain. All right, that's correct. So we can get the current count, and now we have 1. All right, so that's an example contract. So I'll share the Solidity docs and then another resource which you can use to learn alongside. All right, so let's go on to learn about immutable data on the blockchain, and then variables and constants. So in Solidity, we have 3 different types of variables. So we have local variables, we have state variables, and then we have global variables. So the local variables are declared inside of a function and then are not stored on the blockchain. Then we have state variables. They're declared outside a function, but in a contract and are stored on the blockchain. So this is an example of a state variable, the count, because it's stored on the blockchain. And then we have global variables. We don't use that in our contracts because they provide information about the blockchain itself. So we're not going to be using that here. So the global variables are variables like the current block timestamp, the message sender, which is sent on successful transactions, and then other variables. So let's go on to constants. So constants are basically variables that cannot be modified. So if we had a constant here, instead of count, would have defined the exact value of count, would have given it a value, maybe 1 or 2, and then it will not be immutable. So let's go on to immutables. Then immutable variables are basically like constant. They can be set inside a constructor, but cannot be changed afterwards. So let me give an example of a constructor and an immutable constant. So let's say address public. Let's call the address let's call the address my address. Then let's call the constructor, which you can use to modify the immutable. All right. And in the constructor, we can now give my address a value. Let's assign this to whatever address sends the transaction. And then let's give my uint okay. I think we may not need this currently. So let's leave that empty and then only try the constructor and the address immutable. So on deployment to the blockchain, this constructor is only modifying my address variable or my address. I don't call it immutable, but then we can only modify my address using this constructor that we set here, and then set my address to the value of whatever address sent the transaction. This is not relevant to our counter contract, so we'll just be explaining other types of other needed terms in this contract. So we've explored reading and writing data to a state variable using this function. The get function reads data from a state variable. In this case, our state variable is the count variable. And then we also have the function to write data to a state variable. This is our increase and our decrease function. Basically, reading and writing is, for writing is updating data or changing the data on a variable. In this case, our variable is count. And then for reading is to get the current value or get the current data stored in whatever variable we're looking at. So in this case, our get current count is the function that reads data from the state variable. So I mentioned earlier that to read or to get the increase and decrease functions, you need to sign transactions. So reading data on the blockchain or reading data on state variables are free. So you don't need to confirm a transaction. There's no transaction fee. But then writing data to a state variable is not free, which means you need to sign or send a transaction. All right. So I also explained Ether and Way earlier. So these are the basic values. So transactions are paid for with Ether. Then on various blockchains, like on Ethereum, 1 Ether is 1 Ethereum. And then the smallest value is Way, which is equals to 1 times 10 raised to the power minus 18 Ether. So 1 Ether is 10 raised to the power 18 Way. So one thing that is also relevant to Solidity deployment is gas and gas prices. So if you remember earlier on, we had the TX.gas limit I mentioned. So that's relevant, tells us how much gas is being used or the current gas limit on a function. And then if that gas amount is exceeded, the transaction is failed and doesn't get stored on the blockchain. So we can also get the current gas of transactions on the blockchain. So gas basically is the amount of Ether you need or the amount of Ethereum you need to pay for a transaction. So you pay gas spent times gas price. And then the total amount, the gas spent is the amount used in a transaction. And then gas price is how much Ether you are paying per gas. So in cases where we have congestion on the blockchains, gas prices are higher. So cases where there are too many transactions on the blockchain and blockchain validators have to select transactions in order of priority. Transactions with higher gas go first since they are more rewarding to block explorers and block miners. So transactions with high gas get validated first. And then in that order, transactions with mid gas fees are next, and then the ones with lower gas fees come later on, probably when the blockchain is less congested or free. So in our solidity codes, there are gas limits, which is the max amount of gas that a user is meant to pay for a transaction. So that's set by you as a developer. So we can use the gas limit. So usually the gas limit is 21,000 whey. And then there's the block gas limit, which is set by the network itself. It is the current maximum gas fee, which is possible to spend on a transaction. So that cannot be exceeded by a user. Right. So in Solidity, similar to other languages, we have if-else statements, we have loops, like for loops, while loops, we have maps. So I'll try to give short explanations of them. So while I'm explaining, let me try to open up a resource that might be useful, or rather will be useful to you as a Solidity developer. Uh, okay, Solidity by example. Alright, so this is a resource that would be useful. It helps with live or functional code blocks to learn particular terminologies. So if you're learning about variables, it gives you variables being used in a transaction or in a contract. If you're learning about constants, it shows you constants being used in a contract. Right, so you can go through this, and I'll try to teach from this so you can follow through as well, so that it doesn't just sound like me explaining abstract ideas. So let me explain if-else statements. So if you've worked with JavaScript, you'd have encountered if-else statements. So basically, they are conditional statements that make sure that at least one of the conditions are true, or one of the conditions are valid for whatever is going on at the moment. So you have if, which is mostly the first condition or the first possible value. You have if else or else if in Solidity. That shows that, okay, if the first value doesn't work, try this. And then you have else, which shows that if all the other values are invalid. So let's try to say if a user has more than one Ethereum, maybe run this transaction. If a user doesn't have one Ethereum, but maybe has 0.5, run this transaction. And then if the user doesn't have up to that, then run this. So for the first condition, we use if. So if the user has maybe one Ethereum or more, run this. Else if for the second condition. So if the user doesn't have one Ethereum but has 0.5, you can run this. And then else is, okay, if the user doesn't even have any Ethereum, just run this. So that's an example of if else statement. So here's an implementation of a statement that or a contract with an if else statement. So this is a function called foo. It takes in an integer value called x. It's a public function, and then it returns an integer here. So if the integer we pass in x is less than 10, we return 0. If the integer we passed in is more than 10 but less than 20, we return 1. And then if the integer is more than 20, which is the else condition. So if a value is not less than 10, not less than 20, then we return 2. Does anyone understand what this means, or anyone understands if your statement? Is anyone still following through? All right. So let's go on to for loops and while loops. Okay, before we go with that, let's try this if your statement on our own local blockchain.
Yes, yes, we are following.
All right.
All right.
So let's go on to for loops and while loops. All right, let's compile this and deploy it on our local remix. Okay, so we've deployed this contract. Then let's interact with it. So this function here, let's pass in, okay, let's pass in 9. And then let's call. So remember we said if the value passed in is less than 10, we should return 0. So here we have 0 has been returned to us. So let's try in 11. So 11 is obviously more than 10, but less than 20. So it fits in the else if condition. Let's call again. So we receive 1, which is what we asked our function here to return. So now let's try something more than 20, which should fall in the else category or the else condition. So let's try 50. So this should return 2, which is the current value we asked it to return. So we have 2 returned to us. So let's try to tweak the current contract. So let's say if x is less than 10, it should return a string instead. String type, and then return x is less than 10. If it's less than 20, let's return x is less than 20. And if it's above, let's say x is more than 20. Now allowing us to return a string here. Okay. Let's try to change the values instead. As we're not allowed to return strings. Let's say, okay. So now if a value we pass in is less than 10, we should have 11 returned to us. If the value is less than 20, we should have 21 returned to us. And if the value is more than 20, we should have 40 returned to us. So let's compile this and deploy it again. So we should have the new contract here. So let's try and interact with it. So let's pass in 8 this time around, which is less than 10. So we receive 11. So 11 is our returned value. Then let's pass in maybe 18, which is less than 20. Then we receive 21, which is the value we asked it to return to us. Then let's pass in 30. We should return 40, which is what we asked it to return. So here we have it. Now, in this same contract, there's a function called ternary, which basically does the same thing we declared here. But in this case, now we have only 10 as the value. So this is a shorthand way to write an if-else statement. So if x is less than 10, it should return 1, or else it should return 2. So let's try that. So let's go with 9 and call returns 1. So if x is more than 10, let's try 40. It should return 2 now. So it returns 2. Is anybody following? Or does anybody not understand what happened here? Okay. So if you have any questions on what we've done so far, you can stop me at any point in time, even now, and then let me have your questions and I'll try to explain in the best way possible. All right. So it seems everyone is following and understands what we've done so far. So we've gone through so a quick rundown of what we've gone through. We've gone through the data types, which include our booleans, our strings, our integers, and then the address. We've gone through variables, we've gone through constants, we've gone through immutables, we've gone through functions that read and write data on the blockchain. We've gone through ether and way. We've gone through gas prices. We've gone through if-else statements, So let's go towards I think for loop. So once again, you can follow through with the solidity by example page. So let's go to for and while loops. All right. So solidity supports for, while, and do loops. So I'll try to explain what loops are and then how Solidity implements them. So basically, a loop is a function takes in a value and then it tries to run different variations or different possible functions with that value. So let's say you have a value x, which is a number. So if x is less than 10, we can ask it to run this code or run this possible iteration. If x is maybe 2, we can also ask it to run another iteration. And then if x does not fit any of those descriptions, we can ask it to break or stop the iteration. So we give it a set of values for which x can be valid. And then if x is this certain value, should run this. If x is this other value, should run this. And if x does not fit into our required values, then we can ask it to discard the value and then break the function. So one thing with loops is that they can use a lot of memory, and in return on Ethereum, this can use a lot of gas. So if you have loops that are endless or unbounded, these loops can cause your transaction gas fee to be very high, possibly hitting your gas limit, and then your transaction fails. So for that reason, while and do while loops are rarely used. So those loops are usually memory consuming, gas consuming, and expensive in most contracts. So they are barely used in Solidity. So this is an example of a for loop, which is the most popular variation of loops used. So what this loop does is that it takes a value, which is an integer, and then these are the possible values. So if the value received is less than 10, you should increment the value by 1 and then run this following possible code blocks. So if after receiving the value, increasing it by 1, the value that you receive is 3, then you can continue to the next possible function. Then if the value received is 5, you can break the loop. So continue asks you to go forward with the next iteration, since functions are usually run in like a top to bottom manner. So from the first function down to next and down to next. So if your loop or if your value fulfills the function or fulfills the term meant here. So if your value is 3, you can continue to the next function. If your value is 5, you exit the loop, basically. And then we use continue to continue with the next iteration of code. And then we use break to exit the loop. So basically, breaking the loop means the transaction is failed, or whatever you wanted to achieve is not within the range of values you set, and then cannot go forward. So you break it. So while loops are basically not used here because these are like endless loops. So this is a while loop below. So for this now we see that we receive a value j, and then for the whole time, if j is less than 10, we continually increase the value of j until it is 10 or above. So why we mentioned that while loops are memory consuming and can be very expensive is, let's take this for example. Now you have this while loop here, but you change this to maybe 1000. It means that if someone passes in a value 1, it continually increases by 1 until it gets to 1000, which of course would hit your gas limit and probably fail, or most likely fail. So this is why it's not in use mostly. All right. So does anyone have an issue with the loops here? You need an explanation. You can type your responses in the chat if there's a lag. All right. So next we can go with mappings. All right. So next, let's go forward with maps. So maps are created with the syntax mapping. Then we define the key type, then define the value type of that map. The key type can be any built-in value type, byte, string, or any contract. The value type can be any type, including another mapping or an array. And mappings are not iterable. So basically what this means, or an illustration of what this means is the key type can be any built-in value. So want to map a unit to an address, map from an address to unit. So we define the key type here, which is an address, and then define what the value should be, which is an integer or unit 256. And then this map, we call it my map, and is a public map. So we can interact with the map. We get the address, and then we return the value or the address that was passed in. We map it into this map here, my map. And then since we already have a key type, we just map the address that was sent in to the map here. So we can update the value using this, and then we can reset the value to whatever it was by default. I don't know if this is clear to anybody, or I should try to explain further. So, okay, to explain this better, I would have us run the map and interact with it.
Yes, it's clear. It's clear.
Okay, to explain this better, I would have us run the map and interact with it. Okay, so we deployed the mapping contract, then can interact with it. Let me get an address. Now let me set this. All right. So what I did here was I set a value, this, to the value of this address. So let me try to change this to a number instead. So I'll remove the one I set before. And then I'll try to set it again. Let's give it a value of 100 or 1001. So we've set that, and then we can get the value of that address we just passed in. So see it here, 1001. Then we can also remove the value we set for that. So now that we removed it, if we try to call or get the data, we see that there's nothing stored there. So it's 0 by default. Is it clearer now?
Yes, please. It's clear.
All right. Let's go forward to arrays. I explained arrays, but I didn't give an illustration, so I think this should help us. All right. So this is an example of an array. This is an example of an array that takes in numbers. And then this is an example of an array without a set or fixed value. So for this particular array, we can decide to set whatever values we want later on. And then we can also perform computation on this array. So this is a function that returns the total values in an array. So we can get the array, and then we can also push or add data to an array. So increase the array length by 1. Then we can remove the last element from an array. So these are modifier operators by default. So I'll explain what these modifiers mean and what they do. So array.push adds whatever value you are passing in to the predefined array. Array.pop removes the last value or the last element from the array. Array.length returns the total length of the array. So if we have 3 elements or 3 values in the array, when we run array.length, it returns 3. It shows us that, okay, the values in the array are 3. Is that clear? All right. So we explained enums earlier, which are enumerables that have set functions or custom functions, custom values that can only be assigned to the particular enum. So if we have an enum here, we have an enum called status that can only take these following values: pending, shipped, accepted, rejected, and cancelled. So by default, the value of an enum is the first value. So in this case, the first value is pending. So by default, if you interact with the enum, the first value you have is pending, and then you can later update the value or the status to whatever you need. So whatever value you are passing in or whatever value you are trying to update must be one of these custom definitions we have. So if you're passing in a value that is not among this pending, shipped, accepted, rejected, or cancelled, it's going to reject that and it's not going to be successful. All right. So is that clear? All right. So next we have value types that can be defined by you or custom value types. So this is an example of a custom value type or user defined value type in this case. So here we have type, duration. So basically this is the declaration of the custom type duration,
Yes,
which must
yes.
be an integer. So next we have And then we have the custom value type timestamp, which must also be an integer. But then this is an integer with the size 64. That's byte size 64. And then an integer with the byte size 64 as well. But for next, the clock type, we have integer 128. So you can then use these custom types in your code block or in your functions or in your contract, however necessary. All right. So I mentioned structs earlier, and I mentioned that they are like objects in other languages, or they're literally objects in other languages. But then we can define different values under a struct. So here we have a struct named to do. We can then define the text. Text is a value under the struct. Completed is a value under the struct. And then we can have the different types for those values. So we have the value string for text. So the text string the text value itself must be a string. So whatever you're passing in to be used in the struct for the type string must be, for the type text rather, must be a string. And then whatever you're passing in for the completed value must be either true or false. All right. And then you can create an array of to-do structs. Whatever you want to do with structs, you can actually pass them in. All right. So I'll just try to explain. I'll not follow this chronologically, so I'll just go towards the ones that are useful to us right now. We've had a look at functions where we defined the counter function in our counter smart contract here. Then we've had a look at errors. We've had a look at events. We've had a look at constructors for modifying immutables. Okay, now let's go towards interface. So interfaces basically help you interact with other contracts. So let's say you have a smart contract or you have a program you're developing that requires you to have more than one smart contract file. You can use interfaces to interact with other smart contracts in your project. So interfaces cannot have any functions implemented. So they're basically to interact with this other smart contract. They can inherit from other interfaces. And all declared functions in an interface must be external. You cannot declare a constructor in an interface, and then you cannot declare state variables. So basically, all you have to do is interact and gain data from another contract. That's basically all it does. You can't really use it to modify something else. You can't use it to define a function. Is that clear? All right. So over time, we mentioned payable in our contracts. And I mentioned that payable basically means that the smart contract can receive Ethereum, but for a function, basically means that the function can send or transfer tokens. So this is an example. Then, okay, let's try to run this example so it doesn't just seem like abstract explanations. All right. So this is a contract called payable, and then here we've declared a variable or an address called owner, and then we've made this a payable address. Also, we've declared a constructor here. So this constructor can receive Ethereum or Ether because it's a payable constructor. Then we have a function to deposit tokens. So we see function deposit, which is a payable function. So to call this function, you'd pass in some amount of Ethereum, which is automatically going to be deposited in the contract. So this is a function that is not payable because we didn't declare the function alongside the payable keyword. So if you call this function along with some Ethereum, it's going to declare an error and fail. So this is a function to send Ethereum. So all payable contracts can actually send tokens. So this is an example of a function that sends tokens from the contract balance. So next we'll look at sending Ethereum from a contract. So I'll explain that in depth here. So you can transfer Ether by three methods or three inbuilt methods, which is transfer, send, and call. And then we've mentioned receiving Ether already, which is by declaring the payable keyword. So transferring of Ethereum from a contract mostly throws in an error if completed. Sending throws in a boolean, which is yes or no, which shows whether it was completed or not. And then call forwards all gas or sets gas. So these are examples of functions. So this is send via the transfer call. This is transfer. So you can use this. You pass in the address which you want to transfer to, and then you send the tokens with the transfer keyword, and then this transfers to the address that was passed in. Then you can also use the send keyword. You pass in an address to your function. So send returns a Boolean value indicating either success or failure. So he sends whatever amount or whatever amount of tokens or Ether is in the smart contract to the address you passed in alongside. And then you have send via call. This also passes in the address as a required parameter, and then sends the tokens to that address which you passed in earlier. All right. So let's try to look at what ABIs mean. So ABIs basically are interfaces that help you interact with a contract that has been deployed already. So if we deployed a contract, let's say for all the contracts we deployed earlier, we have these JSON files which contain the ABI. So these ABIs are basically required for interaction with any smart contract. So we have the counter.json. Then if we scroll down, we'd see the ABI. Yeah, here we have it, the ABI. So this contains the names of the functions, the inputs, what we have to pass in, and then what we'll receive after calling whatever function it is. So we have the count function. It doesn't receive any value when you call it, but then it returns uint 256, which is an integer. Then we have the function decrease. But we're also receiving nothing since there are no parameters for calling that function. There are also no outputs when we call that function. All it does is to increase the value of the current count by 1. And then it's non-payable. Then we have the type function. So we have inputs already also. This is the get function that gets the total count number. This is also the increase function that increases the total count on the blockchain. So it also takes in no inputs, returns no output, is not payable, and is also a function. So this is an example of ABIs that we receive from a smart contract that has been deployed. This is also an ABI for the if-else function or the if-else contract we deployed earlier on. You also see the functions we have, the inputs, the outputs, for the two if-else functions we declared. We have also for mapping. Then this is also the API for mappings. And for every contract to deploy, we have the ABIs. So for contracts, the ABIs can also be accessed mostly on the blockchain. So after verifying and publishing your contract, you'd have the contract ABI for other developers to interact with. Right. Does anyone understand what we've done so far? All right. So while building on Ethereum, there are a couple of things that are needed for us. So I'll explain what they mean and the different types of contracts basically that we can use or we can have. So we have ERC20. ERC20 is the default token standard for Ethereum. So most tokens are actually ERC20 tokens. We also have other token types. We have ERC721, 1155. Recently, we've had the one for smart wallets. I think that's 4337 or so. All right. So let me try to explain what these are. So any contract that follows the ERC20 standard is an ERC20 token. So the ERC20 standard is declared by the Ethereum Foundation in EIPs. EIPs stand for Ethereum Improvement Proposals. So this is the token standard. And then these are the methods that must be fulfilled in the contract for it to be declared an ERC20 token. So it's the token itself must have a name, must have a symbol, must have a number of decimals, usually 8 or 18, must have a total supply, must have the balance of method or function. We must have a transfer function, meaning the token rather must be transferable from one wallet to another. Must have the transfer from function, approve, allowance, and then must have the transfer or approval event. Then we also have ERC721, which are mostly for NFTs. We have the ERC720 as well. Then we have ERC1155. So basically, all these meet certain standards which have been set by the Ethereum Foundation in the EIPs. Then this is for gasless token transfers. Okay, so let's try to write a smart contract together. Let's say, let's go with the crowdfund. All right. So we'll try to work on this together. So let's try to work on this without looking at the guides provided. All right. Okay. So first thing we need to do after creating our file, let's say crowdfund. So we'll declare the identifier SPDX identifier. Then we have our pragma directive. Let's go with 0.8.36. Then would declare our contract name. Start. What functions would we be needing? I don't know if it's possible for us to interact directly from the Filecoin Builder Hacker House. So, Enoch, is it possible for us to hear from people at the Hacker House as well? I don't know if that's echo, but let's see if it works. All right. Okay. So we'll interact with interfaces. So we need a transfer and transfer from interface. So let's go with that interface IRC 20. So for a transfer, would need the address and then the amount to be transferred. Int 26. Then this can be called externally and returns a boolean. So whether true or false. So the next function is a transfer from function. This also takes in an address and then amount. Int, sorry, int 256. It's also an external function and returns a boolean as well. Alright, then we can go on to work on events needed in our contract. So to launch a crowd fund, you need a launch event. So let's define a thing or two. Let's define the ID of the crowd fund. Let's define the creator. Would also define the goal, which is an integer. So if the goal of the crowdfund is maybe 2 Ethereum, this would also be passed in. Then the time you int 32 for the crowdfund to start and then to end. Yes, start time and then time. So we also have an event to cancel the crowdfund. This takes in the crowdfund ID, which was passed in on creation. So to interact with the crowdfund, you also need to pledge. So this takes in an address, takes in an ID. So if you're pledging into a crowdfund contract, you'd pass in the ID of the specific crowdfund you're trying to pledge to. So let's pass that in. Pledge. So for on pledge, we're also taking the same thing. So I'll just copy and paste this, then change the name of the event. Then in events of a refund, we'd also create a refund event. Okay, 6. So that should be ID, address, which will also be indexed. And then the amount you are being refunded. Then finally, you can claim from the crowd fund. All right, so what we've done so far is to create events for launching a crowd fund, pledging to a crowd fund, and then also unpledging from a crowd fund. We've also created an event to cancel a crowd fund and then refund or claim your rewards from a crowd fund. So we'd go on to create a struct which would define a campaign or a crowdfund campaign. Then would create an immutable that creates the token for the crowd fund. Then we also create a count. 6. This is to show us the total address, the total number rather of crowdfund campaigns created. So if you remember earlier, we said um you can map the value of you can map a value in a map to another map. So that's what we did here in this line 36. So we'd also create another constructor that modifies the immutable we have above. So we'll start with the functions for our crowdfund. So we create a function to launch a crowdfund. So what then now is to assign values to a specific campaign. So assigning the creator the goal, the amount pledged, the start time, end time, and whether the crowdfund rewards have been claimed or not. So we're going to also use this. This is using the values from the struct we created earlier. So remember in our struct, we have the value creator, which is an address. We have the value goal, pledged, start time, end time, and claimed. So I'm going to do that here. So this assigns the value of the creator to whatever address initiated the transaction. Then the goal assigns this to whatever value was sent in. We assign the pledged to 0 because on start of a crowdfund, it should be 0. Then start time, we assign this to whatever start time was passed in to the function. And then end time to whatever end time was also passed in to the function. And then we also assign claimed to false since it's a newly created crowdfund campaign. And then we also emit to our events we created earlier. All right. So what I did here was to emit the values. So this is the count, which also is the crowdfund ID. So this is continuously incremented. So on every new contract or new crowdfund campaign that has been created, we add +1 to the IDs stored in the contract. And then also store this as the ID of the crowdfund that has been created. Then we also pass in the message to sender. So we're making use of this event we created earlier, the launch event, which emits the ID, the creator, the goal in amount, of course, and then the start time and end time of the contract or of the crowdfund. So this is what we're emitting here. The ID of the crowdfund, the creator of the crowdfund, the goal of the crowdfund, the starting time, and the ending time. So in this launch function, we pass in the goal, which will later emit the goal of the crowdfund. We pass in the starting time of the crowdfund. We pass in the ending time of the crowdfund. So we made sure that the starting time of the crowdfund is greater than the current block time. So it cannot be in the past. And then the end time of the crowd fund cannot be less than the starting time. So you cannot end a crowd fund before it's created. Then also make sure that the ending time is less than 90 days away. All right. So what we then did was to add whatever campaign we just created to the campaigns map that we created previously. So this is the campaigns map that we created. And then whatever new campaign we create just now would be added to that map. So let's also go forward with the cancel function. So if I created a crowd fund and I want to cancel that, I can make use of this function. So we pass in unit 256, we pass in the ID of whatever contract wants or crowd fund we want to cancel. Then this is also an XNow function. Then we initialize the function. So we'll check the campaigns we have from the memory of the contract for the specific campaign ID. And then we'd make sure that the campaign creator is also the same person that is trying to cancel the campaign. So we'll do this. Campaign as creator is equals to the message sender. And if not, it emits not creator. And require. This is also to make sure that the campaign had previously started. When timestamp is less than campaign start time. So if all those requirements have been met, you can then delete the campaign. Then we emit the cancel event that a certain campaign has been cancelled. All right. So this is our cancel function and should work properly. So we'll also go towards the few functions left. We should have a pledge function for people who want to pledge. So let's create that. Pledge. Yep. Let's pass in 6 and call that ID. Let's also pass in an amount. So if I want to pledge an amount, I'll pass that in as well. And let's make this an external function. So anybody can contribute to this. So we'll check our storage. Paying for the particular campaign that has been passed in. Then we'd make sure that the current blockchain timestamp is greater than the current the block or campaign start time. So that's to make sure that the campaign you're trying to pledge to has already started. So let's do that. Block the timestamp is greater than campaign dot start time, or else we'll return the error campaign not started. So we'll also try to make sure that the campaign has also not ended. Require lock the timestamp is less than campaign dot end the time, or else we'll say campaign has ended. All right, and if all those have been met, then we can go towards pledging campaign dot pledged. Then you add the amount that has been pledged in. And then also update the pledged amounts. Pledged amount ID. So what this did is to add in the amount that was pledged alongside the message sender, which is the person that is trying to pledge, and the ID of the crowdfund campaign we're trying to pledge to. Then would also transfer the tokens from whoever is trying to pledge to the contract. Then transfer the same amount. Right. And once this is successful, we'd also emit our event pledge, and the ID of the transaction, the caller, which is the message the sender, and the amount that has been pledged. Right, does anybody understand all that has happened so far? Is anybody following?
Yes.
Yes.
All right. So let's go forward with the unpledging function. So to unpledge, we'll take in the crowdfund ID. So take in the amount you want to unpledge and 6. And then we also make this function external. So anybody can call this function. So once again, would check our stored campaigns for the current campaign ID that has been passed in. So I'll just paste this so no waste time typing. Then also make sure that the campaign has not ended. So is this. Then if those have been fulfilled, then we check the campaign pledged amount, campaign dot pledged, and then we minus the amount that the person wants to unpledge, and then transfer token transfer to the person who is unpledging, then same amount. Okay, before that, we have to update the pledge amount in our campaigns so we don't make mistakes. So we pass in the ID of the crowd fund that we want to unpledge from. We pass in whoever is unpledging, and then we update that minus equals amount. All right. So once this is successful, we can also emit an unpledged Then we pass in the ID of which contract or crowd fund we unpledged from, whoever called or unpledged from the contract, and the amount that the person also unpledged. So that's our unpledged function. Then let's try the claim function. So if the crowd fund is successful, let's try to claim our tokens. So passing the crowdfund campaign ID, and then make this callable by anyone. So we'd also check our storage for the campaign ID. And then make sure that it is not the creator trying to claim the tokens. So require if the campaign dot creator is the message sender, let him know that campaign creator cannot claim receipts or claim rewards. Also check to make sure that the campaign has ended already. So let me just do this. Then also make sure that the campaign goal has been met. Campaign dot pledged is greater than the campaign goal, or else you tell them that pledged amount is less than the goal. All right. Then we'll also check to make sure that the campaign has not been claimed from campaign.claimed. So what I'll do here is to make use of this. And then if it's been claimed, we let them know that proceeds have been claimed. So if all these conditions are met, then we'd set the campaign dot claimed to true. So it updates to make our contract know that this crowdfund campaign has been claimed from, and then we transfer the tokens to the campaign creator. And then the campaign amount, campaign that's pledged. All right. And then we emit an event that lets us know that we have claimed from that crowdfund. All right. So we can also work on the refund function in a case where the crowdfund was not successful and we need to refund to users. So once again, we check our storage for the particular campaign in question. Then we let them know that the campaign has not ended. Make sure that's compulsory. And then make sure that the goal for the campaign has not been met. So require campaign that pledged is less than campaign goal. So we'll also make sure that the balance of the contract, the 66 balance is the pledged amount. Of the sender. And then would also change the pledged amount from that particular sender to 0. And then we transfer the tokens to the user. Set the sender. And then once this is successful, we should also emit an event that lets our contract know that this crowd fund has been refunded to this user. And then the amount. All right. Does anyone understand what we've done so far?
Yes, yes. Hello, yes, we understand.
Yeah, I get you. All right.
Uh,
So let's go on to deploy. Would compile and deploy this on our test network. And then we'll deploy this as well. Not allowing us deploy. Okay. It's not allowing us to deploy one at a time. All right. So I have succeeded in deploying. So let's try to interact with our crowdfund contract. So we can check the counts. Currently we have 0 crowdfunds. So let's try to create a campaign. We'll launch a campaign. So let's say the goal of the campaign should be 1 Ether. Then what else do you define? The start time. Okay, we meant to pass this in current time. Can't get the exact time. Okay, let's do this. Okay, it failed because the time I put was less than the current time. Let me try to get the current time. All right. Mm. All right. So I've launched a campaign, and then you see that our current campaigns are one. So let's try to make sure that the time is reached. So we can now pledge to a campaign. So pledge, let's say to campaign one, then pledge 1 ether. Okay. Transact crowdfunder pledge code, error code. Okay. An error code. Red transfer transmission select code function should be less than current balance. I think it's less than current balance. 0.2. Oh, okay. The campaign has ended. So the time I put is quite short. Let me create a new campaign to let me what's the current one? Let's say 2400. And then the ending time should be 2500. Or 15 to 500. Oops. What's happening? Two, four, two, three. The time I'm imputing is quite correct. I don't know why I'm having the issue. Okay. So that's created. Let's try a new one. I'll try to pledge. The campaign not started. So let's wait a bit till the campaign is started. So you should start in about 1 minute. All right. So let's try to transact again. Oops. Pledge rather. The code function should be payable. Okay. So it seems we did not declare payable in our function. So that was giving an error. Right, so let's compile again and redeploy. Now let's try to launch another campaign on our new contract. Right. So let's wait for about a minute as well before the campaign time starts. All right. So let's try. Let's pledge 1. Value should be less than your current balance. think that's less than my current balance. If for some reason it's not transferring Ether from our test account, all right. So does everyone understand what we've done?
Yes, I understand now. Yes, I understand.
All right. So I would share a couple of resources to Enoch, who would get them across to the hacker house.
Okay, just try. Maybe one day.
No, no.
Hello. Are you enjoying the session? You're following. Don't mind also. You're also following.
So I'll
Yes.
share a couple of resources to get them across.
Hello.
Yeah.
Okay. Yeah, you said you'll be sharing some couple of resources. I don't know if you can share them on the chat so we can get them personally, and also you can still do likewise as you said, so that we can also revert back to the resources which you said.
Oh, okay. All right. No problem. I'll share them on the call here and then still send them to Enoch.
Okay.
Yeah. Think submitting by example. Then Solidity docs. So for both links I shared, you can read through over time, and then if there's anything you have an issue with while reading through, you can pass them to Enoch or myself, and then we'll address them. All right. So over to you, Enoch.
Right. Can you hear me? Hello?
Is echoing on your end? So
What about now? What about now?
yeah, it's still echoing.
It should be better right now. Can you hear me? Huh? Can you hear me? Okay, if you can hear me, just let me have, can you just do an emoji, something?